Imagine a machine so small it fits in your hand, yet powerful enough to challenge the limits of reality itself. This is not theory or speculation, it is reality. In December 2024, a quantum chip called Willow solved a problem in under 5 minutes, a problem that would have taken the world's most powerful classical supercomputer, an estimated 10 septillion years, to complete. That is not simply faster, it completely redefines the scale of what we believed computation could achieve. And when physicists examined the results more closely, something did not add up. Not metaphorically, but physically. The computational resources required for such a calculation do not appear to fit within the limits of a single universe. So the question is no longer how fast this chip is. The real question is, where is the computation actually happening? When Google introduced Willow, the headlines focused almost entirely on its speed, 5 minutes versus 10 septillion years. But speed is actually the least remarkable part of the story. The true anomaly lies in the sheer scale of the computation. The number 10 septillion is so unimaginably large that it loses all practical meaning. It is not just beyond human timescales, it exceeds cosmic timescales. Even if every computer ever built had been running continuously since the beginning of the universe, they still would not have completed the task. Yet Willow did. This is not like upgrading from a bicycle to a jet. It is more like stepping completely beyond the boundaries of the map. Earlier quantum processes, such as Google's Sycamore chip, hinted that this future was possible, but there was always debate. Perhaps classical computers would eventually catch up. Perhaps the gap was not permanent. Willow erased much of that uncertainty. The difference is no longer simply a race in speed. It represents two fundamentally different ways of performing computation. Classical computers work step by step, following a single path from one calculation to the next. Quantum computers operate in an entirely different way. They do not simply move faster. They explore an enormous landscape of possibilities all at once. That is where the story becomes far more intriguing. Willow is not merely solving problems more quickly. It appears to be using a computational space so vast that it seems impossible to fit within the physical limits of the chip itself, or even within the observable universe. A classical computer behaves like a disciplined thinker, making one decision at a time, one step after another. No matter how fast it becomes, its process remains fundamentally linear. A quantum computer is something entirely different. Instead of using bits, it uses qubits. Unlike ordinary bits, which can only be either 0 or 1, qubits can exist as both 0 and 1 simultaneously through a phenomenon known as superposition. This allows a quantum system to represent many possible outcomes at the same time. The true power of quantum computing emerges when qubits become entangled. When that happens, the system does not simply double its capabilities, it grows exponentially. By the time a quantum processor reaches more than 100 qubits, as Willow has, the number of possible quantum states becomes unimaginably large, exceeding even the estimated number of atoms in the observable universe. Think about that for a moment. We now have a machine capable of processing more possible states than there are atoms available to physically represent them. That creates a fascinating paradox. If a classical computer performs all of its work locally inside its hardware, then where is a quantum computer carrying out such an enormous amount of computation? The physical chip itself does not appear large enough to contain all of those computational possibilities. This is the point where physics begins to blur into philosophy. For decades, one idea has quietly existed within quantum physics, the many-worlds interpretation. According to this theory, every quantum event creates multiple branches of reality, with every possible outcome occurring in its own separate version of the universe. To many people, this sounds like science fiction. Yet some physicists, including pioneers of quantum computing, take the idea very seriously because it offers a possible explanation for a genuine scientific mystery. Where does quantum computation actually occur? If every possible quantum state exists in its own branch of reality, then perhaps a quantum computer is not performing all of its calculations in one place. Instead, it could be distributing those calculations across many branches of reality simultaneously. Imagine facing a problem so difficult that solving it alone would take longer than the universe has existed. But the instant you begin, thousands, millions, or even trillions of versions of yourself appear, each solving a different piece of the puzzle. Somehow, all of those answers are then combined into one final solution. that is no longer just the plot of a science fiction story. It is one of the more intriguing ways some physicists interpret the behavior of quantum systems. And Willow has brought that discussion from the realm of abstract theory into serious scientific conversation. If the computational resources required for Willow's achievement cannot fit inside a single universe, then perhaps they are not all coming from one. While this remains an interpretation rather than an established fact, it raises profound questions about the nature of computation and reality itself. The mystery becomes even deeper when we consider another essential feature of quantum mechanics: interference. Quantum computers do not simply explore every possible solution. Different quantum states interact with one another, reinforcing correct answers while canceling out incorrect ones. This process, known as quantum interference, is what allows the system to arrive at the correct result. But interference requires interaction. If those quantum states truly correspond to different branches of reality, then what exactly is interacting? Within the many-worlds interpretation, those branches are not merely mathematical abstractions. They represent separate configurations of reality. Interference becomes the moment when those branches overlap just enough to influence one another. It is not communication in the ordinary sense, nor is it the exchange of messages across universes. Instead, it can be viewed as a shared computational process that spans multiple branches of reality.